Yeah. So today I would like to talk about cryptography, namely about how developers screw cryptography. I have to say that it's not an easy task to talk about cryptography. I would say it's similar to the fact that not every developer or somebody who's just writing their own code is interested in security. Similarly, not every security-minded person is necessarily interested into all aspects of cryptography. So if you take all these people who are interested in IT, then you have a very small area which are interested in security, and then I would say there are also only tiny amount of people which are interested in cryptography. So it's a very challenging task to talk about it. So I was thinking about how to approach it today, and usually when you come to talks like this, there are two types of talks. Like, one of them are more or less inspirational talks, and people are trying to convey some very high-level thing to people, or they go really deeply into details and they try to show some vulnerability, something very specific, where the audience is usually very small, but of course interested in these kind of things. So today I tried to kind of give you a little bit of both. So I'll talk a little bit about details, about crypto details, but not as much. But I also want to convey some something to everybody of you, something that everybody, even people who are not really crypto researchers, who are not really interested in security, can use every day. So, what does conventional wisdom tell us about security? Like, I think most of you already heard like, please do not implement your own cryptography. Don't deal with crypto. Crypto is dangerous, and everything is really negative. But then, every day people write code, and more people use cryptography. There is a lot of push to make things secure, and to encrypt stuff, and store it, address encrypted, and transfer data encrypted, and everything encrypted. But at the same time, we hear like, please don't use cryptography because you screw things, and so on. So I think this is contradictory. People do write code, and no matter what, they need to understand cryptography. So I think this is a very challenging task. And then another thing is that whatever people write, the code is really, it's not tested enough. I think one thing is that penetration testers, they mostly focus on things which are exploitable very easily, or not really easily, but they can show the impact so easily, like cross-site scripting and these kind of things. But I think they rarely really spend enough time to challenge cryptographic encryption. So I think that's also one thing. And also, cryptography is now used almost everywhere, but it's also almost everywhere broken. So we live in a world where people think like, oh, everything is encrypted, but if you really scrutinize things, in many cases you just find that we are not doing a good job. There is, this is from the last Veracode's report from June. It shows, Veracode is a company which does static code analysis. So it looks for vulnerabilities in code, and then they also provide these reports about like what are the most common vulnerabilities found by them. It's partially done by, of course, static analysis tools they have, but they also run their consultancy, and they do manual reviews. So it's not only based on automatic findings from software, which very often give you false positive things, but actually on their own experience. And you can see that it's divided per different industries you have, and you can see in certain industries cryptographic issues are actually the most common issues. For example, in healthcare industry, where there is big push to encrypt stuff because, of course, this kind of data is really sensitive. So what is actually the problem? Why do we have so much code which is broken? I think one thing is that it's something I already mentioned. It's that developers always hear like, don't deal with cryptography, and they are kind of scared of that. And then there's a different group of people who do something with crypto, and they kind of feel comfortable with that, and they think they can do it, but actually, no, they cannot. And it gives them this false sense of security that they are good, but they're actually not. So you have these two groups of people who kind of live in this world, and they produce code, but ultimately it's insecure. There is another thing, and I think this is not only about people who develop code on a daily basis for production purposes, but it's also about people who actually do crypto research, who write crypto libraries for use, because it's similar to how everything in IT, actually everything in IT up until now was developed by geeks. I think now it's a little bit changing, and not everything is developed just by geeks or for geeks, but I think you can think of it the same way in crypto world, where most of the crypto libraries are just written by cryptographers or people who actually understand crypto very well. But those are usually not people who mostly use these libraries. So a lot of libraries are written this way, and then it's actually assuming a lot of knowledge about cryptography. And actually, in most cases, a lot of knowledge you might not necessarily have to develop this kind of feature which encrypts something. So all these libraries, or most of the libraries which are used nowadays, are very low level, and they give you a lot of free room to do things, to change things, and if you don't understand what you are doing, you can screw things easily. So I think another part of this issue is that actually we are giving people who don't really understand the stuff the opportunity to work with these things. So, and also, I forgot to say one thing. It's cryptography. I think it's also very problematic in a sense that most of the code people write today, if something is broken, you can usually tell. Not easily, but most of the times you can tell. And you have good methodologies to test code and do these kind of things. But if you screw cryptography, sometimes it might be invisible. You may have this false sense of security that everything is protected properly, but actually it's not, and it might not be that obvious. So I think that's also something people need to understand. Yeah, and then people also don't understand how much knowledge they need to have to do things securely. And again, we are at a point where cryptographers say, oh, don't deal with cryptography, but people also don't know what it means. Whether it means just don't touch cryptography at all, but this is unrealistic because people need to develop code, right? They need to develop stuff which uses cryptography. Whether they just shouldn't develop their own crypto primitives, or whether they just shouldn't use low-level libraries, and these kind of stuff. So it's not well defined. And they actually don't have choice. People just have to develop this kind of thing. So what's the way out of it? And what are the points I would like to emphasize in this talk? Of course, the first and utmost important is to train developers, to show people how to do it right. And I think a good way to start is to show how people actually screw things. Because I think that you learn the best from mistakes. And the second point, and I think this is just a side note, it's something also I already mentioned, and I'll also talk a little bit more about that. It's the importance of using the high-level libraries we have, or at least even work towards having these libraries, because in some cases we don't have these, and that would be the message for people who deal with cryptography as their main job. Yeah, so again, this presentation is mainly about these 2 points I just mentioned. So what kind of issues we have in cryptography? Bruce Schneier, a very famous cryptographer, in his essay he outlined several types of cryptography errors or attacks against them. And I won't definitely touch all of them. I will mostly focus on these first 3 things, because those are things which cryptographers deal most with. Those are issues with cryptographic designs, with passwords, and with implementations. Because I think since developers are told to not implement your own crypto, I think we are more or less secure in this regard. People don't, especially experienced people, that usually don't develop their own homebrew systems. They do sometimes, but I think nowadays it's less and less common. But what they actually deal with is that they use crypto primitives, crypto libraries, which use more or less secure algorithms, but the way they are using them, it's insecure. So I will now cover 7 areas which I think are the most common. I'm not a cryptographer, and I'm not doing any specific research in cryptography, so all I'm going to talk is about mostly based on what I've seen code people wrote. So just take it as it is. So first area is really juicy one. It's improper password storage, and it's really interesting that these days where almost every web service, everything is based on some kind of passwords people use. It's still in 2015, password authentication is the most common authentication we have, and it's the issue of storing password has been known for so long, and even though the protection developed a little bit over time, or the way we protect it developed over time, the concepts are still same, and people are still screwing the same way. And actually using the libraries we have and the design patterns we have for storing passwords is not so complicated. I'll just give you a couple of examples. I don't know if you remember this from news. In 2012, there was a big hack of LinkedIn. Their passwords got leaked. There was more than 6 million passwords. And since these passwords were not protected securely, the attackers were able to basically ungarble the hashes and find the original passwords that they used. Why? What went wrong? So first of all, they didn't use any salts to solve their passwords. I don't know. I hope that everybody kind of understands the concept. Just reiterate, salt it's a value which is usually appended to the original password before you store it in a hash form, and it's mostly done because you want to fight the rainbow table attack. Rainbow table attack is an attack where you basically pre-compute all your hashes, and then in exchange for the storage, you save the computational time. Second thing they did, they used SHA-1 algorithm. SHA-1 algorithm, first of all, it's being phased out, and it's not considered secure anymore, or not secure, but it's not considered cryptographically strong enough to be used these days, but mostly for things where you need to do some sort of signing. But there is also another issue why SHA shouldn't be used for password storage, and it's the fact that it's actually very, very fast. And it's a problem, because these days actual rainbow table attacks are not such a big issue, because in the past the storage was actually very cheap, and it was cheaper than computational power. But nowadays with cloud computing and these kind of things, it's actually vice versa. So the importance of being protected against rainbow table attacks is decreasing, but what's even more and more important is actually protection against brute force attacks, and that's the situation where we really need to have slow hashing functions, because they protect us against these things, and that's what LinkedIn didn't do. And then when attackers got the DB, they were actually able to get the passwords. Another one, and it's a recent one. It's actually, I don't know how many of you noticed this in news. It was on all news in the United States. Actually, Madison, it's a dating site mostly used by married people. Basically to cheat on their wives and stuff like that. And they got hacked again. And since maybe some hackers had this moral issue with the site, they said, okay, if you don't shut the door if you don't close our business. We will make all the things we stole from you public. So, and they did. And they did, and the DB they made public also included all of the user passwords. And not only that, it included credit card data, payment data, their emails, their sexual preferences, and these kind of things. And so it was it was covered by press a lot, I would say. But just getting back to what happened with their passwords. So initially everything seemed pretty fine. They said, oh, we have these, they have the password hashes, but we protected them according to the standards. We use this bcrypt algorithm, which is actually a slow hashing algorithm I was calling for. It's an algorithm which allows you to define certain cost factor, and it applies many rounds of hashing before it actually computes the final hash string. And that way it makes the whole process very slow, and that way it's also hard to get the original password back. However, they did a mistake, and that's what I was talking about initially, that sometimes people use everything which is secure, but then their architecture sometimes introduces a weak point. And in this case, they, for some, I think it was actually for a feature to keep you logged in, they computed another variable called login key, and it was based on the MD5 version of the original key. And they stored several millions of these keys, and attackers were again able to produce the original keys this way, because they were using MD5 algorithm, which is a fast one, and there was pretty much no issue to them to use cloud computing and clusters to compute it. There is a site run by Troy Hunt. It's an Australian security researcher at IBM Pumped, which actually collects the information from all these big breaches, including, you can see here, you can see there was Adobe breach, more than 150 million accounts got leaked, but also this Ashley Madison is included, Snapchat, and all LinkedIn is included. You can go there and you can check if you've been humped or not. So what's the way out of it? How can we do it securely? So of course, we don't store passwords in plaintext. We need to hash them. That's obvious, and I think most people understand that. But what they don't understand is two things. You, of course, need to use salts, which is important, but as I said, not as much as it used to be in the past. But even more, we need to use slow hashing functions. There are several of them, and each of them has different advantages and disadvantages. The PBKDF2 has been used a lot in the past for this purpose. It's still used for different things, but for password storage, it is not used as much. Bcrypt is, I think, the function or the algorithm of choice these days, but it has one disadvantage over Scrypt, and that's the fact that you can use computing power which is very cheap, but doesn't have much memory, much operating memory. And you can compute these hashes with bcrypt very fast, because bcrypt doesn't actually need much memory to do all the computational work. For that reason, there is a new algorithm, or relatively new algorithm called Scrypt, which kind of also requires a lot of memory, but it has one disadvantage, and it's a relatively new thing. And in cryptography, people tend to not use stuff which is very recent, because, as I said initially, with cryptography, it's very easy to screw things, and it takes a lot of time to actually prove that the algorithm withstands the crypto attack. Sometimes you never know whether the algorithm is broken, but of course the more time you have to break it, I think people can be a little bit more certain that things work. So Scrypt is not used as much because of this reason. Another thing, and I think this is important when you're designing your system which uses passwords, is that you shouldn't be allowing people to use weak passwords. Even with Ashley Madison case, before the researchers found out that there was this issue with using MD5, they didn't know that initially. They were able to compute a lot of these hashes because people are of course using these passwords like 112 or 123 or password and this kind of stuff. And you as a designer, you might be asking, why would I make this forbidden? Why wouldn't people allow people to use these passwords? I think if your service becomes publicly so well received and will be used by many people, over time you may deal with things like fraud and people complaining about being hacked and about bad publicity. And I think you can limit this threat by imposing certain rules on like what kind of password people should use. Also, another issue is that people doing crypto, and especially with passwords, they keep the passwords in memory even if they don't use them. It's a similar issue as cryptographic keys are kept in memory. I think that's also something when you're doing a design to kind of focus on these kind of things. So I just, since I was talking a little bit about high-level approach, I just included how PHP encrypts passwords, and you can see that they are actually getting closer, a little bit closer to the state I would like to see, and that's where people are actually not thinking about how long the key should be, what the IV should be, and these kind of things, but they just have an API which they can at least rely on, and they can use it. And for example, in PHP, you have this password hash function where the cost for the slow hash, even if you don't define it, is by default secure. And I think that's the way to go. So another thing is improper use of hash functions. So what do people do wrong with hash functions? So it's 2015, and MD5, as you could see in Ashley Madison case, is still present in a lot of code, even though it has been considered insecure for many years. I know there are instances where the weaknesses of MD5 are not such a big threat, but still I think we shouldn't use these functions, because if people are not able to clearly say that in this application MD5 is secure, I think they should never use it, because it makes just things more complicated. Same situation is with SHA-1. It has been broken, it has been thought to be broken for many years, but even up to these days we have certificates where the signature is done using SHA-1 and so on, and SHA-1 is used a lot. Another issue, and I will talk about it, is what people do wrong when they are comparing hashes, since it's acceptable to timing attacks, and also that using certain hash functions might allow a length extension attack. That's also something I will cover. So comparing hashes, I don't know how many of you would find this construction insecure. But actually it is. The problem is that if you're in a situation you accept a hash from insecure or like provided by some insecure, untrusted source, and you want to compare it to a hash you store, let's say, in the DB. Most of the times, or very often, people just use the standard API they have in whichever platform they work for, and they just do a comparison. But you know, the standard crypto is not done for this purpose. The fact is that it's designed in a way to work very fast. So for example, if you are comparing strings, usually it's implemented in a way that whenever you find a character which doesn't match the original string, the process finishes and it returns that they are not the same. And you can use this fact for timing attacks. You can basically be sending certain hashes and see how fast it takes to the system to respond that, okay, this hash is not valid or mismatch or something like that. And based on these, you can actually get the original hash. So this is one thing. Length extension attacks. This is related to one thing I was also talking about, and that's that sometimes people use cryptographic primitives or crypto algorithms for what they are not. For example, in this case, they are using SHA-256 for keyed hashing. But they are doing it in a way that they actually include that key and concatenate it with a value inside the function. And this construction proved to be insecure because it leaks. For certain hashes, you can, as an attacker, you can provide your own hash with appending certain value to the original one, and you can get a hash which is actually signed by the original key you don't know. So, for example, in this case, you had a value which was sent $100, but any attacker with very easy procedure can append 0 and can compute a hash which actually passes the signature check. And you can read more about it in the blog post I included, because, as I said, I cannot talk about all the details here, because just this algorithm or this attack would take, I don't know, 20 minutes to explain. So, the right way to do it, I think it's very simple. Don't use insecure hash function. Don't use MD5. Don't use SHA-1. If you need to do signatures of this type, signature you want to verify yourself, and you want to do this key hash algorithm, use HMAC. Ideally, HMAC with SHA-2. And if you want to compare hashes for some reason, I hope it's not needed as often, but if you need it, then use the API which is used for that. So before you do that, research whether the API you use is actually designed for that. I also included one example in .NET here. So another issue is using encryption without authentication. It's very popular misconception that people think if they encrypt stuff that it also provides authentication, meaning that if I give you my encrypted string, you cannot do anything to it to actually impact the encrypted string. But actually, it's actually in some situation it's easy, and there are even nice attacks with this. I think most of you have seen this in the basic crypto 101. This penguin, I think, is a very popular image. When we work with block ciphers, most of the people understand that using the electronic codebook is not a secure mode of operation. You can see what it causes. Basically, the same string is encrypted to the same ciphertext, and based on that, you can infer a lot of information about the original string. Like, for example, visualize the penguin here. So that's why people introduced this concept of IV to the block ciphers. So we have a CBC mode of operation where you actually, before you do the initial encryption, you XOR the IV with the plaintext, and it makes sure that basically two ciphertext with two different IVs that are encrypted in two different encrypted texts. Oh, sorry, the plaintext encrypted disks are in a different ciphertext. But what people don't understand is that you can actually, without any authentication check, you can do this. It's called Bitflipping or Bitflipping attack. What you can do is that you can choose any block in that encrypted cipher or in that ciphertext. You can flip the bit. It garbles the plaintext for that block. But in some situations, like for example for certain web services, you're sending some data, you don't care that this part at the beginning will be nonsense, but you are able to flip the bit in the other block which is following to it. So say you would have a service with when this parameter was 0, you would grant access, and when it was 1, you would not. And with this bitflip attack, you can garble the text before, but you can actually change this. And the receiver of it, if it doesn't perform any authentication check of that message, it's tricked. It thinks that he was the one who encrypted that and he's decrypting that. So let's say you have a cookie, you think, oh, I'm going to protect this kind of data, this token, and I will send it to the user, and then since encrypted, the user doesn't understand anything about it, and then whenever he provides it back, I will just give him whatever he wants. But it's acceptable to this bit flipping attack. Another thing is padding oracle. Padding oracle is an attack which is very, or is usually successful against a lot of, or has been successful against a lot of web applications in the past. So when do we have padding oracle? So you have a service which encrypts something for you. You send it to the user. And whenever user sends the data back, you don't perform any authentication check on the data, meaning you didn't verify that the data actually was encrypted by you. The attack is called padding oracle. It's commonly found using the mode of operation I just showed, CBC mode of operation, counter block changing, or IES. Since this mode of operation doesn't do any authentication checks, and with the padding, with the standard padding we use these days, this padding information can be sometimes exploited. How it's happened? A lot of services, whenever they are accepting this string, they do a check whether they can decrypt it or not. And they do check whether the padding is correct or not. And if it's not, they usually reveal that information to the user, saying, oh, padding was incorrect. And if padding is correct, but something else happened, they also provide this information to the user saying, no, padding, in this sense, padding is okay, but some integrity problem in that hash. And this might not necessarily be in a form of a text message or something like that. This can be also inferred based on timing. So any attacker can observe, hey, this responds to this many of milliseconds, and this responds to this many of milliseconds. And you can, based on that, you can say, oh, this was probably issue with padding, and this was probably an issue with some integrity. And using just this, there is an attack using this padding oracle, where for any ciphertext, you and with possibility of calling this service and sending the service this ciphertext and checking whether the padding was correct or not, you can actually decrypt the original text, and actually pretty fast. It's also an issue which was part of this Poodle attack against TLS, if you if you remember from last year. So how to do it right? How to fight against this? So of course I said, and I mentioned that we have modes of operations which actually provide authentication. CBC doesn't, and CBC is used very often, but it doesn't provide this. We have, for example, GCM, which provides the authentication check. Not authentication check, but it provides the authentication, authentication, you can call it. Like, basically, it doesn't, it wouldn't decrypt the message if it detects that the message actually was not encrypted by your secure key. If you don't have this possibility of using this kind of mode of operation, you can also apply HMAC. It's not ideal. There is a lot of people argue whether it's better to HMAC and then encrypt, or encrypt and then HMAC, and some people will tell you this is better and this is not better for these kind of reasons. And I think just to avoid this, you can use the mode of operation which provides the authentication, and you don't have to involve in this discussion, but it's still better than nothing, I would say. Another issue, we're using nonces and IVs. A lot of people use the word nonce without knowing what it actually means. It means number used only once. And yet, so many people are using these. Also, IVs. IVs usually need to be random and also unpredictable, because it might cause problems. One very common, or not common, but well-known problem was in the web protocol used for Wi-Fi. And the issue was that RC4, which is a stream cipher, which was used to encrypt the payload, actually in the original design or in the algorithm, it doesn't deal with the IVs. So actually, the way it's used in web was that the IV was part of that seed with key. And that seed also was not long enough, so it left only 24 bits for that IV. And 24 bits, it's not enough space to provide you, to actually provide you, or to ensure that you never repeat that value again. And since RC4 is a stream cipher, and for stream cipher it's very important that you never repeat the same, or you never use the same key to encrypt the string, then this caused trouble. There were passive attacks which were just waiting until you exhaust all these random values, and then you reuse the IV again. But then, of course, people got more creative, and they applied active attacks, and also some other issues found later allowed them to decrypt the traffic. So it's one of the examples where IV was being reused. So, what's the right way to do it? Whenever you encounter with nonces, please don't reuse them. They should really be used only once. Not always they need to be random, not always they need to be unpredictable, but all the time they just need to be used once. For IVs also, the situation in certain scenarios is a little bit different. Sometimes they need to be unpredictable, sometimes they not, but usually if you have a random IV, you should be safe, which is unpredictable. Also, sometimes people, when they are using, for example, CBC algorithm, they for certain reasons they need to have the same text encrypted the same way because they want to query some data from DB, and they need this kind of thing. And they tend to use just a static IV. So for everything they encrypt, they use the static IV. And that way you actually end up with very similar situation like using the electronic codebook, where every string would encrypt to the same, using the same IB and using the same key would encrypt to the same ciphertext. And that's what you don't want. In certain situation, it just reveals the beginning. In certain situation, it reveals everything encrypted. So yeah, just don't do it. Another issue, dealing with randomness. So randomness is an integral part of most of the crypto systems or crypto algorithms we use these days. We rely in a lot of instances on PRNGs or random number generators. And we really need to use them securely. And also it's a thing people have a lot of misconceptions about and they don't understand. And lots of issues are based on either using wrong sources of randomness or just completely omitting randomness or limiting randomness to actually very, very narrow or very narrow data pool. One of these examples, for example, the famous one was the bug in Debian used to sign, the code used to sign certificates. It had a pool of entropy which it needed to receive or feed in, and then basically by commenting one line of code, because there was some software which complained about it, they encrypted it out, and what it caused is that the only source of entropy was the process ID, and that's not many values you can have. And basically what it caused with every certificate issued here, or even key, which was then used to sign something else, need to be revoked. Another instance was the PS3 console, which was hacked. It has the design on paper didn't look really bad, but when people were reversing how PS3 is signing some high-level operations, it actually figured out that the source of entropy for that signature was static. So basically, it was using the same value for every signature. And that way, again, it allowed the reverse engineers to crack it. Another thing, what people do wrong a lot of times, it's modulo bias. So let's say people already chose good source of randomness, and they get a value, random value from good source of randomness, but that value, out of that value, they need to get just they have values which can occur, but they want to limit the values they want to get out of it. Like, for example, you want to generate a string, a random string, and based on all these characters which are there, you want to pick only, I don't know, readable characters or something like that. You can represent that, of course, as numbers, but the issue is still the same. So, for example, in this situation, you are generating random values 0 to 3, but you used a rand function which gives you values 0 to 5. So what is a very common mistake is that people apply this modulus and they think, yeah, now I'm in the range I want, I'm generating only 0 to 3, and this modulus allows me to get rid of the values I don't have. What they don't realize is that it causes this so-called modulo bias, which occurs anytime when your maximum value plus 1 is not evenly divisible by 2. And what happens is that if you use this modulus to get the values you want, then certain values can occur more frequently. For example, 0, there is a chance 40% that you get 0 out of 0 to 5 modulus 4. There is 40% you get 1, but there is only 20% you get 2 or 20% you get 3. And what it does is that if you need to get a random string, which I use as a key or something, then certain letters, or certain letters may actually occur more often, and it allows attacks which guess these strings, and they can basically the values which are more often, they can actually guess these more often, and they get more information about it. So it's also not good. Of course, a simple fix would be that you would compute actually the excessive values which get over these maximum value plus 1 modulus, and then you would just whenever you get over that limit, you just discard the value and you search again. That would be just a simple fix, but yeah. So the right way to deal with randomness, use crypto APIs and crypto libraries which really give you random or pseudo-random data which are fitted by good sources of entropy. I just included a couple of examples. Also, there is a common misconception on Linux that you shouldn't use the /random because the urandom is sometimes blocked, and then there is a lot of discussion about whether this is an issue or not, but actually you can get it as certain that urandom is considered, like in most cases we use it a good source of entropy, even though it's unlocking version. Unlocking means that whenever the pool of entropy is exhausted, it still gives you the values. Another failure, very common, is use of TLS certificates, namely validation of TLS certificates. TLS was originally designed, or actually used, mostly in browser connections. But over time, we use SSL these days for mobile applications. We use it for backend communication. And a lot of people need to implement SSL. So what they do, they think that, okay, I use this library, this OpenSSL, it's all secure, I'll just get the code, I'll turn something here and there, and yeah, some certificates are coming, I'm verifying it maybe, I don't know, the library uses it somehow, and they think they are secure. But actually, no, there are a lot of issues with this, and there is really good article about it. There is a really good paper, this one. It's called the most dangerous code in the world, validating SSL certificates in non-browser software. And the people examined web services, very high-profile vendors, Amazon and so on. They found that even in these instances, the SSL certificates were not verified properly. Common mistake is, I see it very often, people say, hey, I'm having SSL, I'm validating the certificate, but what they don't understand what actually valid certificate means, or what validation of certificate means, or what they really want to get. They make a certificate which is valid, but is it really valid for their use case? Is the subject actually a subject they want to communicate with? This is something people very often misunderstand. So they basically establish a SSL connection, they get a certificate, they check, oh yeah, it's signed, everything is fine, but they don't actually check whether that entity is the entity they want to communicate with. Also, revocation check, very often omitted. I think a lot of people also in the past use OpenSSL library, which I think is horribly documented. They don't even know that SSL or revocation check is not enabled by default, and that you actually have to even download the serial file to perform the revocation check. And that's also a reason why many people are not even enabling the revocation check. Also, common mistake is that people, when they are doing testing, they disable SSL traffic completely for, I don't know, testing purposes. Then they forget to enable it again. Or they just disable certificate validation and then never enable it again. So, what's the way to do it right? So first of all, of course, I think everybody needs to understand how certificate works, what's in there, what I really want to validate. I think that's the first step. But then, also very important, you need to rely on some sort of unit testing when you implement this. You need to, and especially a negative one, you need to check, hey, with this kind of certificate, I don't want to communicate because I don't trust this issue. With this kind of certificate, I don't want to communicate because this subject is not the subject I allow. I don't want to communicate with this kind of certificate because this is not the certificate, the root certificate, and so on. And you need to really have these tests in your code, because that way you can actually make sure that it's implemented properly. There is a site called www.betssl.com where if you need certificates for certain scenarios, you can get them and they will allow you smooth testing. They of course don't cover all scenarios you might have, but I think they may help you with many instances. You can get expired certificate, brown post, self-sign, and so on. Also, I think nowadays people shouldn't say, hey, we are not using SSL because getting certificates is expensive and so on. There's an initiative called Let's Encrypt, which actually has a goal to provide free certificates. Now it's in beta version, but I think soon it should be available with everybody. And after this, I don't think there will be any reason to not use SSL and to not use SSL securely. Last thing I have, it's insecure key provisioning. We talked about randomness. Randomness, of course, is one integral part of crypto system. But keys are the other one, right? Because most of the modern algorithms or crypto systems, they rely on the fact that the key is kept secure. And very often you can see nice design, the algorithms are good, the way they are connected and they are used, it's more or less fine, but then nobody really thinks about what's happening with the keys. And if keys get leaked, then everything is broken, right? So oftentimes keys are stored on developers' machines, they are hard-coded in code, and so on. There was, this is an interesting article I found. In 2013, GitHub allowed a new search feature. And very fast, it turned out that using this feature, you can search for keys which are actually uploaded to, or committed to GitHub. And I think somebody ran an analysis and found thousands of AWS connection strings and RSA, private keys, and so on. So you can see this is actually proof that people are hard-coding keys or are storing them insecurely. So, what's the way to do it right? Again, don't hard-code your keys. Don't store them on insecure places. If you have a design which relies on keys, and it almost always relies on certain keys, really think about how you can rotate the keys. You can think ahead about what you can do with these keys. Because when something happens and you start thinking about, hey, now I need to rotate the keys, I think it's actually very late. Of course, not always you have all the technology to store the keys properly, but I think you can always do better, a little bit better, and you can think things through. Yeah, don't do things like reusing keys for multiple purposes, different devices, and so on. So what are the takeaways? What I wanted to convey today? Yeah, of course, don't develop your own crypto primitives, but I think most of the people realize that. Now, I think if you are well trained and you understand these crypto concepts and you're a decent programmer, you can deal with cryptography. But you need to really spend some time to understand the fundamentals. And also it was what I tried to convey, that we didn't really study details of all these attacks and things, but whenever you deal with these things, I think at least if you have this red alarm in your head saying like, hey, yeah, I'm comparing strings, maybe I should search again how to do it properly. Oh, I'm working with this PRNG. Is this library secure or is it not? And so on. Then another thing are these crypto libraries. And I think it's a lot of mess because people don't understand which libraries they should use. There are many of them, and OpenSSL is quite famous, but I think it's horrible. It's horrible to use it in a lot of things because, as I said, it's designed by geeks for geeks. It's designed by cryptographers for cryptographers. And if you have possibility of using more high-level library, I think you should always resort to using higher-level library because, first of all, they are based on these more low-level, usually low-level libraries. But the API doesn't offer you so much choice that you can screw so many things. One example I just provided is this project from Google. A couple of years ago, they basically created a high-level library called Quitzar. It covers multiple platforms, Java, Python, C++. And the whole goal was to actually provide a high-level API and not give you opportunity to screw things. It also has a port to .NET, Quitzar-.NET. You can find it if you need it. Just an example how encryption works with Quitzar. You create a new object, cipher, you load the keys, there is already some information about the algorithm which is used, but then simple cipher.encrypt, and you provide a secret message and everything is encrypted. And you really don't need to think about much about the algorithm, about the keys, about, you know. So, of course, it doesn't fit all scenarios. If you want to control the length, if you want, you know, you have some certain format specification, this kind of thing, it doesn't fit all scenarios. But I think in 80–90% of scenarios when people are encrypting data, they can just use this and be secure, have some knowledge of fundamentals, know that, you know, how this works, but they can actually use crypto and not worry so much. I also wanted to provide some recommended resources, which I think that are good. Any developer to follow. It's very, very good source is the Matasano Crypto Challenges. Matasano it's an American company, like a security consultancy, and they created this set of crypto challenges where you basically always have some goal to do or correct something, and usually with just a couple of lines of code you can do it, but with doing that you just get much better understanding. And you don't need to have much knowledge of cryptography. I would say actually almost no knowledge before you start these challenges. I think you learn everything with that. Also there is course on Stanford, cryptography. I think the second version on the second version. The following course, Cryptography 2, is starting in January. And also, if you want to follow some good blog from Schneier, it's the Schneier on security. And I think that's it. So if you have any questions, feel free to ask them.